Good afternoon, mathematicians. I hope you guys are watching this on Tuesday, November 3rd, and you guys have already voted. You guys are great citizens, if you are 18, of course. So, since today's class is asynchronous, we're going to wrap up section 3.3, which is what we're on now. We talked about percent change versus average rate of change. So just a quick recap. Average rate of change, we're pretty familiar with that, just the slope between two lines. Where percent change, we had f of x plus 1 minus f of x over f of x. So that percent change in it. And we looked at last time where exponentials are going to have a constant percent rate of change, but linear functions we know have constant average rates of change. And we talked about that here. So we did a few examples. I messed up my numbers, so my example actually didn't work. Whoopsies. So now let's do some actual examples from the book that I know will work. So we're given that city officials in Newburgh population is 10,000. They wish to make a long-range plan to maintain, expand infrastructure and services to their city. Great, right? We all took the census. So they hired 2 city planners to construct models for the growth over the next 5 years. So planner A, let's see. Planner A estimates the city's population is going to increase by 500 people per year. So each year, I'm just going to add 500 more people. And then the city population, Planner B, says that the city population is going to be 5% per year. So if we were in class, I would ask you guys, which type of models should we use for A and B? Since we're only increasing by 500 people, a specific unit, that's a constant average rate of change. So this is going to be a linear model. You guys are also going to see all my colored pencils. And since it's a 5% per year increase, this is going to be exponential growth or an exponential function. Right? Because we know when we see percents, that's a really good sign of exponential growth or decay. So let's focus on planner A first. So planner A, it's a linear model. So linear models, let's call this like population of sub A, so P sub A over this specific time. That's just what we're going to call our function. So we know that linear models look like y equals mx plus b. So we're just going to call this mt plus b, right? M is our slope, and b is our initial condition. So we're probably going to take the fact that our initial value, time t, is kind of where we're starting right now, which I think is currently at, what's a neutral color? Ooh, I can use this pink now. Still can't really tell. But that 10,000 is going to be our initial for both functions. They're just going to look different. So that's telling me that b equals 10,000. Since I'm taking time 0 as like currently. And then we'll talk about happening the next 5 years. So if I'm going to increase by 500 people each year, that's going to look like, right, I have 10K now. In 1 year, I'm going to have 10,500. In 2 years, I'm going to have 11,000. So that average rate of change of 500, I'm just adding 500 for each year. And that actually tells me that the slope, that m, is actually going to be 500. And if you wanted to work this out, work out the math and do like 10,000 minus, I did this backwards, but that's fine. 10,000 minus 500 over 0 minus 1, you'd get negative 500 over negative 1. which equals 500. So that's our slope. So I can write that P of A T, so the population from planar A, I can model it by 500T plus 10,000. Great. So now for B, planar B, he said that it's going to grow, it's going to increase by 5% every year. So kind of think about an investment is my recommendation right now. If I want my portfolio to grow 5%, I want that to be my growth rate or my growth factor. I'll give you a second to think about that. Okay, growth rate or growth factor. Lock in your answer. It's 5% the growth rate or the growth factor. It is the growth rate. Right? Kind of think of it like your interest rate. My interest rate is 5%. I'm still going to have that 100% still there. Nothing is going to be taken out, and I'm just going to have another one, right? Because remember, we have this fun little equation that A is R plus 1. My growth factor, remember A is before R, so our growth factor is A, equals 1 plus our growth rate. So it means that A would equal 1 plus 0.05, because that's how we talk about percents and decimals. So 1.05 would be A. I kind of jumped the gun. I was really excited about that. Remember, exponential growth and decay, we can both model it like this. We know growth here, it's increasing, so that's a really good indicator of growth. So that means that A is going to be bigger than 1. That's another way to check yourself if you're like, ooh, which one is my growth rate versus my growth factor? 5%, 0.05 is definitely not going to make A. It's not going to be greater than 1. Add 1, then it is. All right, cool. So I have C 1.05. Oh, actually, I don't have an X right here. I have a T. Oh, I was still writing with my eraser. T. So C, remember, is also our initial condition. So C, initial condition. Great. So our initial condition, remember, is the same for both of them. It's 10,000. So P B of T equals 10,000, 1.05 T. So those are our two models. We love them. They're gorgeous. They're the best. Okay, great. Now we're asked to graph the two of them next to each other over the 25 years. And then if we were in class, we would discuss how they're different. I'll probably have to beg someone after a while to give me an answer, but we'll just work with it. So I like to use the same color blue as my graphs. Not this one, that one. So why does that not look straight? Boop. Okay, great. And so we start at 10,000. So let's kind of just make this 10,000. And I actually don't need all this space because we're only talking about time being greater than 0. So 0, call that 10,000. So let's do wrong green. Let's do A first, P sub A. So 500T, so over the next 25 years, so many colors. So we're going to have 5, 10, 15, 20, 25. So at 0, we know that we're going to have 10,000. After 5 years, I'm going to have 5 times 500. Just plugging 5 into our function. 5 times 500. So I get 2,500 plus 10,000, which is going to give me 12,500. So I'm just doing this to get a point on the graph that I can then kind of go like, oopsies, right up here. And after 25 years, oopsies, 25 times 500. I'm doing this on my calculator by hand. You cannot see that. I get a total of 22,500. Sorry, I changed colors. So that'll be like up here, right? Yeah, we'll go right there. And this is just going to be a straight line. Well, actually, it's just going to go wherever that line is. There it is. So now for, let me go in the right color, T, 0, 5, and 25 for piece of B. Again, I know it's 10,000 when I start. Then I have 1.05 raised to the 5th power times 10,000. And that's going to give me about 12,763. I just rounded up. I just put that in my calculator. And then if we did the same thing for, if I put 25 in for T, we would get 33,863. So at 5 years, we're just a little bit like so negligible above. But after 25 years, we're like all the way up here. So our graph kind of looks like this. Let me try that a little bit better. And it's going to get faster and faster. Oh no, I didn't want to do that. Okay. Whew. Panic. Right, so how are they differing? Green, obviously it's just a straight line. But their differences at 5 years is 263. But after 25 years, they're over 11,000 different. So the discrepancy between them is growing. All right. So if I was scrolling too fast during these and you kind of missed something, I will post these after I'm done recording. So they're already posted when this video is posted. All right. So next, a cell phone company holds 3 million phones this month. Or they sold 3 million phones. But the company president would like for sales to double their efforts and double sales every month. This means that sales would grow exponentially, right? I'm doubling. So if I sold 2, then I sell 4, then 8, and then 16, and so on. If this were to happen, they would nearly sell 12 billion phones in the 12th month, and then need to double it. That's more people than there are on Earth. I think there's like 8 billion, almost 9 billion people. So an exponential function's not enough, right? I can't sell, no one's going to buy 2 phones. I mean, you might. So we're going to have to change it around a little bit. I like this purple color. We're still going to use some parts of an exponential, but we're going to change it up a little bit. So we have something called logistic growth. All right, and it's a model of the function of the form. Sorry, it's a function of the form. That's what I meant to say. We have c divided by 1 plus b times a raised to the negative x. Only a is raised to the negative x, right? So in this case, a is greater than 1 and b is greater than 0. And we'll talk about what all these things mean. And this models growth under limited resources, right? So cell phones being sold, I can't sell but so many. A lot of the time, population of like a certain animal in a certain area, depending on resources. And I'm skipping ahead. Okay. So x again is the number of time periods. Kind of similar to how we were talking about growth and decay. C is not the initial condition. C is what we call a carrying capacity. And we've mentioned this word before, I believe. Carrying capacity is the maximum population resources can support. You might hear some people talk about population of the earth, the carrying capacity being a such and such amount due to how much we can farm, how much land is like available, clean water, and stuff like that, right? So, and the graph of this doesn't look like our normal exponential, right? Because it's an exponential growth. So, draw my little axis. Boop. Okay, great. And let's keep this being purple. So our function's going to kind of look like this. And it's going to keep going. I'm going to retry to draw that. Actually, no, I'm happy with that. And that's f of x. So notice that it doesn't flatline necessarily, but it's just kind of like slowly approaching this line. That's actually c, right? Y equals c right here. That's that line. If this point is c, it's an asymptote. Asymptote. A-S-Y-M-P tote. If you ever heard a function be asymptotic, it's one of my favorite words. Asymptotes are just lines that a graph can usually never cross. This one is a horizontal asymptote because it is a horizontal line. And this is just right as this function goes off towards infinity and t goes off and towards infinity in time, I'm going to get really, really close to that c, but I'm never really going to touch it. Like I can't ever really touch a cloud. It's like the cloud line, something like that. Okay? So let's work through a model. I hope you guys have heard of asymptotes before. It's such a fun word. All right, so a biologist models the number of fish in a small pond by the logistic growth function. So we have, what do we have? I have 100 right here. That's my carrying capacity. 1.5, that is my, well, it used to be my growth factor, but now we don't know. I don't know what 9 is, and I don't know my initial condition. We're going to figure that out. So a biologist models it, so 100 divided by 1 plus 9 times the quantity 1.5 to the negative x. X is the number of years since the pond was first observed. Okay? So let's keep with this mossy green. I vibe with that. Okay, cool. So the initial number of fish in the pond. How do we find the initial number of fish in the pond? I can't just look at the graph, the function. It doesn't really tell me anything. How do I find Yes, I want to set x equal to 0. Duke, you're fine. Duke wants to go outside. So I need to find where f of 0 is. So I have my function. I'm going to plug 1 plus 9 times 1.5 to the 0. Only 1.5 is raised to that 0 power. Anything raised to the 0 power is just 1. We learned that at the beginning of class. So I have 100 divided by 1 plus 9, right? Times like 1, basically. So that's going to equal 100 divided by 10, equaling 10. Great. If we wanted to look up at our traditional function, this guy, our initial condition or initial value is going to be your carrying capacity over 1 plus b. I don't know why. I don't make the rules. That's just what it is. And you can look at that where, right, 1.5 is our a, but it's okay. Come here. A is 1.5, right, negative x, but that's 0, so that goes away. So that can be our initial condition. Great. What is the carrying capacity? Well, that one's not too hard to find. That's just that top number. Did I need to give you all that space? No. I'm actually going to show a little bit more work. I like when you guys show me a lot of work. So I'm going to show you guys some more work. So 1 plus, what is it, 9? 1.5 to the negative x. So C equals 100. And the carrying capacity is 100 fish. All right? So now we're asked to make a table and graph the function. I was so generous and gave you this. So this would be the time that I would ask you to pause the video, plug in all these numbers for fun. I'm just going to write them right now because I have them all written. So we have 10. That's where we started. We already calculated that one. And then I'm just going to plug in each of these year values in for x. So 14, 20, 27, 36, what's 5? 46. Duke. He was literally chilling, taking a nap all morning. And now he's like, I gotta go, Mom. My doggy friends. So after 20 years, we've hit that carrying capacity of 100. Obviously, I rounded. We're never actually gonna hit that number. Big yawn, but there's only so many halves of a fish that I can have. So if I draw boop, my graph, and who's to say we can't have 100 fish? Right, we can only have whole numbers when we're talking about fish. Wow, that was beautiful. Because we're modeling real world phenomenon with some fun numbers. All right, coolio. And that's what our graph's gonna kind of look like. All right, cool. So that's actually going to wrap up everything that I really wanted to talk about in this section. So we are going to, I've been timing. We have 50 minutes left of kind of like our allotted time. So I probably don't want to use all of that time, but let's move over to 3.4. That is not today. I did take the pumpkin patch out. I'm very sad about it. I guess it's still fall, so I can have pumpkin patches, but yeah. again, if you felt like I was rushing stuff, you can always just like pause this video. I'm also going to post it to YouTube. Yada, yada, yada. Okay. So section 3.4 is kind of about the graphs of exponential functions. So we just saw last time the graph of the logarithm, exponential logarithm. What was it called? Hold on. Logistic growth. Excuse me. Goodness. So now we're going to kind of talk a little bit more about graphs and kind of getting a graph from the function or function from the graph. So before we just saw like exponential growth and decay used in the form of f equal to c a to the x, right? We can generalize this. Ooh, what color do I choose? I like this color. So we just say like an exponential function of base a, remember a base a like that, is of the form where a is greater than 0 and a is not 1 and the domain is all real numbers, right? So it's of the form, I messed up my notes, we're fine. F of x equal to a to the x, where this line should be like below here. So where a is greater than 0 and a is not 1, right? Because if a is 1, it would just be like a line. Silly, boring, not fun. And the domain is all real number. I can always plug a number up here. I can plug in a half, I can plug in 1, I can plug in -1, I can plug in pi, and I'll get a number out. I can plug in 0. Right, so now we're asked to graph by hand, so I'm not going to use Desmos or at all to graph f of x equal 2 to the x. So let's make a little table. Boop. Not straight. Okay, good enough. And we're going to have x and f of x. So let's do, 1, 2, 1, 2. Oops, that's out 2. Let's do -2 to 2, and then we can extrapolate from there. So kind of using what we know about exponential growth and decay, do you think this is a growth or decay? Do we think f of x is growing or is it going to be decaying? Two is greater than 1, right? So if we look back at our growth model, we just needed that base number to be bigger than 1, so growth. So this function is going to grow. So we're going to plug in -2, -1, 0, +1, and 2. Duke, what are you doing? Come here. Suspicious about what you were doing over there. Okay, thank you. So if I plug in -2, that'll give me 2 to -2. Well, I know from exponent rules, that's just going to be 1 over 2 squared, which is 1/4. So that's going to be this point down here. And then two to the -1, sorry, it's 1/2. At 0, anything raised to the 0 power is just 1. 2 to the 1 will give me just 2, and 2 squared will give me 4. Right, so we're doubling. I can make that a little taller. Each time. So our graph's going to kind of look like this. And I'll draw an arrow. All right, awesome. So now let's compare to if, right, we talked about this being a growth, but what about a decay? So let's do a twofer, right? We're going to do when f of x is equal to 3 of x and when g of x is equal to 1/3 of x. So when a is 3 and a is 1/3. So let's draw our handy dandy graph. Let's keep this graph. I like it. I really don't need all of that jargon. Can I copy? Copy. Paste. Great. And then I think I can paste right here. Paste. Beautiful. Okay. Cool. I don't want these things. And I don't want these things. So let's go through here again. So if I'm plugging in -2 and 2, 3 to the x, that'll give me 3 to the -2, which give me 1/1/9. 3 to the -1 will give me 1/3. Anything raised to the 0 power is 1. Let's see. 3 to the first power is 3, and then 3 squared is 9. So it's going to look pretty similar to the last guy we drew. Great, awesome. Also, if I don't fill up an hour and 15 minutes, don't tell anybody. We are just going to finish this up. Great, awesome. So, what is happening? Oh, yeah. So, I need to draw these guys. Okie dokie. So, what am I doing? Oh, right, I'm plotting this. Okay, so at -2, it's going to be 1/9. So, like, super small. And then 1/3, a little, 3 times as big. And then 1. And then 3 times as big. And I can't even fit all of it in there to reach up to 9. Similarly, for 1/3, now I'm going to put 1/3 to the -2. Well, that's just going to give me, if I put just that negative inside, remember the negative just flips it, so I get 3 squared, which is 9. Well, then 1/3 to the -1, similarly, is just 3. Again, anything to the 0 power is 1. 1/3 to the first power is 1/3. And 1/3 squared is 1/9. Do you see a pattern? They're switched. So I'm not even going to try to put 9 up on there because I know it won't fit. Oops, that line was not. There you go. So this model is decaying. I drew it opposite way. I drew it right from left, but that's just how you draw curves. So we can see that as x is getting bigger, this one's getting smaller, so it's decaying, and as x is growing, the function here is getting larger and getting bigger. So, right, how do the graphs change as a's change? So, oh my gosh, no, did Notability just close on me? Oh my god, what? Okay, thank God. Jesus. What was I doing? Okay, cool. So, how do the graphs change as a changes? So we know that if A is greater than 1, I'm going to grow. If I'm growing, if it's less than 1, I'm decaying. But what about if I change A, if I'm just looking at different growth models? I say growth models just because I know it's going to grow, right? So now we're going to graph A of X, but when A is 2, 3, and 4. So can I still paste this? No, I totally can. Just wait. Oh, wait, paste it as an image. I don't want that. Haha. Okay, cool. So now we're going to do it all 3 of them. Boop. So we're going to do 2 to the x, 3 to the x, and 4 to the x. I'm actually going to go, I'm not even going to walk through how to do these. We've already done 2 and 3. So this is 1/4, 1/2, 1, 2 and 4, 1/9, 1/4, 1, 4 and 9, 1/16. Oh, that's supposed to be 1/3. I was thinking about 4 too much. Got so excited. This one's 1/4, 1, 4, and 16. Cool, but I can only really be able to tell. We can look at those numbers and it'll tell us something, but I think graphing them is going to help us out a lot. So call that 1, call that 2, -1, -2. Great. I'm getting the most unnecessary emails today. So we'll do 2 of x in this pink color. So let me also do this axis. So 1, let's do, I'm trying to think. Let's do 2, 4, 6. Yeah, okay. So let's start with 2 in this pink color. So I get 1/4, 1/2. There's 1. And then 2. And then 4. And then if we keep going, we get like 8 and something like that. Then let's change, no. So let's do this color for 3 to the x. So we get 1/9, 1/3, still 1, and then 3, and then 9, which would be up here. And then do 4 of x, this deeper blue. It's really, really small. Still small. 1, 4, and like all the way up there. Okay, that green color is not right. No. Oh my god. This is so dramatic. Okay. It's gonna bug me too. Yeah, that one's right here. Okay, there we go. So, as we can see, oh my god, no. Stop. The larger the A is, the faster it grows. right? So they all kind of crossed at 1 right here, or act like they did in the picture. We can see that. But after 1, 4 to the x grows so much faster than all the other ones. But below, 2 is the one that's going to be greater than them all. But you can even just see that it's steeper and steeper. So what do we think is going to happen when c(a) to x? So as we change c. So let's graph f of x equal to c times 2 to the x, with c equaling 1, 2, and 3. So then, let's do the same beautiful picture as we had before. I'm going to keep this, take this with me. Can I copy? Copy. Oh, beautiful. Except I'm going to get rid of, oops, I didn't want that line gone away. And these guys. Okay, great. So let's choose some other colors. So we have 2 to the x, which that's when c equals 1. So when c equals 2, I'm going to have 2 times 2 to the x, and then I'm going to have 3 times 2 to the x, and that's when c equals 3. So let's plug in again. I really actually am just going to multiply each one of these numbers by 2 or 3. So 2/4, that's going to give me 1/2, and then that's going to give me, oops, I'm in the wrong color. This is so ultra confusing now. Remember, this is just like 1 times. So 1/4 times 2, that's going to give me 1/2. 1, 2, 2 times 2 is 4, 4 times 2 is 8. And now, right, because I already know what 2 to the x is for each of these x values, and now I'm just multiplying each one of those by 3, because that's what c does. It just multiplies them by 3. So we're going to have 3/4, 3/2, 3, 6, 4 times 3 is 12. Okay. You just like do so much mental math that you're just like, hold on. Let me check if 6 plus 8 is 14. Okay, cool. So let's like move these dots over. We don't need them so close. So we have -2, -1, 1, and 2. So we have a lot of things under the decimal, but we're just going to keep this 1, 2, 3, and 4. Actually, okay, so then this is going to be 1. Okay, so let's do the pink. So we know this is 1/4. Oh, that's too big. 1/2. 1, 2, and 4. And then it's going to be 1/2. 1, 2, 4, and 8. Act like that was a beautiful arrow. And then for when c equals 3, it's going to be 3/4, 3/2, 3, 6, and 12, like right up here. So neither of them really look too much steeper. I don't know why there's a question mark here. But we can see that as C increases, the function is stretched vertically. So if I think of this pink one as my original, I'm just like pulling it up. I'm stretching it, I'm stretching it, I'm stretching it. All right. Kind of if I like could pull my axis up. You can't see my hand motions. So never mind. Okay, I think this is the last thing I wanted to go over today. It's all that I prepared. So great. So we're gonna find the functions f of x equal to c a to the x from the graphs. So I've kind of used all these colors today. I haven't used, oh, what a beautiful berry color. So we're given these two graphs, A and B, and we're going to find the function f of x equal to CA of x, and we're going to use our knowledge from above and our knowledge of just like some exponents, right? So C we know is the initial condition, right? So then looking right here, initial condition, right? That's when x equals 0. So if I look right here, that's when x equals to 0. So I know that C in this case equals 1. Now I know that f of x is going to equal 1 times a to the x, which is just a to the x, right? So now I have this other point right here, -1 and 15. Oh, not 15, 1/5. And I need to find what a is. I don't really feel like, I'm not told this is exponential growth. I'm just looking at a graph. So let's just plug in these numbers. So f of -1 equals 1/5. And plugging it into the function, that's just going to be a to the -1. Well, I can just solve for a, can't I? If a is to the -1, I can raise everything to the -1 power, which will give me a, and 1/5 to -1 will give me 5. So a equals 5. C is 1. Bada bing, bada boom. I get f of x is 5 to the x. Great. Wasn't too scary. Let's go try this one. This one looks terrifying. Just kidding. It's totally fine. This beautiful gray will work great. So again, f of x equals c a to the x. C is when x equals 0. So it is our y-intercept, which in this case is 3. So I know that my function is going to look like f of x equal to 3a to the x. Beautiful. Now I've done that, I'm going to plug in, I only have one unknown, a. X and f of x are just points. Plug in -2, 12. Right? So I'm going to have 12, equal to 3a to the -2. And we're just going to solve it like we would any old problem. Remember, if you're a little stuck on this kind of type of solving equation, go back to the first few sections we did where we reviewed how to solve like power functions that involve exponents, and that might help you a lot. So we want to do reverse PEMDAS. So I want to get rid of things that are added and subtracted. Don't have any of those, so I'm done with that. Then I want to get rid of things that are multiplied and divided by my thing that I'm solving for. So I divide by 3. 12 over 3 is just 4. Now I want to get rid of our exponent. Negative 2. I want to multiply by the reciprocal of that, which is 1 over negative 2 or negative 1/2. Same thing. So negative 1/2. So A equals 4 to the negative 1/2, which is going to be the square root of 4 to the negative 1. I just put the 1/2 first, which is plus or minus 2 to the negative 1. So it's either 1/2 or negative 1/2. How do I know the difference? How do I know if it's 1/2 or negative 1/2? We're actually going to go check at the top of our notes because we were given that A is greater than 0. So I'm not going to need negative 1/2. So I can just confidently say that A is equal to 1/2. Great. I was supposed to find the function. I found all the pieces. Now I'm going to put them together. A equals 1/2. What does C equals 3? So that is how I get my magic function of f of x equal to 3, 1/2 to the x. And we're done. I don't want to take up a whole hour and 15 minutes for you guys today because you guys might have questions, might have to stop and take time to write some of this. I kind of went through this stuff a little fast. That's just my pace. I can't really stop and ask, oh, thumbs up, thumbs down, that kind of stuff. So hopefully giving you that 20-minute break will let you catch up. We will move on to section 3.5 on Thursday.